Hi everyone. In this video I will be demonstrating how to perform binary logistic regression using Stata version 17. And throughout this presentation I'll be relying heavily on the drop-down menus to generate our output. Now before I get started, I do want to mention that underneath the video description you will find a link to the Stata data file that I'll be working from in this presentation. So you can download a copy of the data to follow along. You will also find a link to a PowerPoint that is going to provide a lot more detail than I'm going to be covering in this video. So be sure to download that to learn more. So before we get started analyzing data, let's consider our data and our examples. So we're going to be working with fictional student data that incorporates this variable pass. So this pass variable is a binary variable that's coded 0 or 1. So 0 indicates that a student did not pass a test, 1 indicates that a student did pass a test. So what we're going to be doing with our logistic regression models is predicting the probability of a student passing a test based on a set of predictor variables. So for example 1, we have 3 continuous predictor variables: anxiety, mastery goals, and interest. And for example 2, we're going to maintain anxiety, mastery goals, and interest as predictors, but we're also going to be adding in a factor variable. You'll see that right here that we have an income level as a factor variable. That variable is coded as 1 for low income, 2 for medium income, and 3 for high income. So you can see that that is an ordered categorical variable. But what we're going to have to do is to ask Stata to convert or transform that ordered categorical variable into dummy variables for inclusion in our regression model. So the dummy variables that will be included are this variable medium income and high income. And the reference category that we're going to be using in this dummy coding system is the low income category. And what that's going to mean in terms of interpretation of the regression slope for the medium income variable is that it reflects the difference in predicted logits between the low income and the medium income groups. And then the regression slope for the high income predictor is going to reflect the difference in predicted logits between the low income group and the high income group. So now let's go ahead and open up Stata and begin running our analyses. So we have Stata opened up with our data, and I'm going to begin by going to Statistics, Binary Outcomes, and clicking on Logistic Regression. So here where it says dependent variable, I'm going to select my binary outcome, pass, and where it says independent variables, I can either type in or select our independent variables: mastery goals, anxiety, and interest right there. Under reporting, you'll notice that by default it's set up to report on odds ratios. I generally tend to prefer to start out with the reporting of the unstandardized coefficients and then proceeding to odds ratios. So I'm actually going to go ahead and select that right here, but that's not a requirement or anything of that nature. That's just my personal preference. So we'll start with that. So we'll click on OK, and we'll generate our output. And so in terms of our output, there's output that's going to be related to assessment of the overall fit of the model to the data, and then there's output that pertains to the individual predictors. So we'll start out by looking at the overall fit using the likelihood ratio chi-square test. So you can see that we have the chi-square value that's given and then the p-value for that test. And so basically with that test, if we find statistical significance, then what that would indicate is that our model represents a significant improvement in fit over a null or intercept only model. And just keep in mind that a null or intercept only model is a model with no predictors. So you can see that we have that situation reflected in our output. We can also from this infer that at least one of our population regression slopes will be non-zero. Then right here we've got McFadden's pseudo R-square value. So you can see it's 0.0634. And when we're talking about pseudo R-square values, just keep in mind that these are considered as analogies to the R-square value that we're used to in the context of linear regression. But it's only an analogy, and you should not interpret the pseudo R-square as indicating the proportion of variation accounted for by the independent variables. So instead, we should interpret this pseudo R-square value, McFadden pseudo R-square that's given, as the proportionate improvement in fit of our model containing the full set of predictors relative to that null model that I was referring to earlier. And so the index of fit that's used in the computation of this is the model deviance, which is given as -2 times the log likelihood. So just keep in mind that there's a -2 log likelihood for the null model and a -2 log likelihood for a model containing the full set of predictors. And basically a zero value, it's bounded at 0 on the low end, and then obviously it gets, that value can get larger in relation to that. But 0 is basically indicating a perfect fitting model. So as we move from 0 in the positive direction, then that's going to indicate a worsening in fit of the model. So we have that -2 log likelihood or deviance value for the null and the full models. And so again, that pseudo R-square value is reflecting proportionate improvement in fit from our null model to our full model. So now looking at the regression output, you can see that we have a column of unstandardized regression coefficients, standard errors. We have Wald z-values and p-values that are given. You can also see we have confidence intervals over here. So we have our predictors, mastery, anxiety, and interest that are given. And so the regression slope for mastery goals is 0.096. It's a positive value, and you can see it's statistically significant. And because that that value is positive for that coefficient, that's indicating that students scoring higher on mastery goals had a greater probability of passing the test than students scoring lower on mastery goals. The negative coefficient that you see right here for anxiety, you can see first off it's statistically significant, and that negative coefficient is indicating that students scoring higher on anxiety had a lower probability of passing the test than students who were lower in anxiety. With respect to the interest predictor, the coefficient is 0.042, so it's positive, but you can see it's not statistically significant. So that's basically indicating that interest is not really contributing uniquely to the model in terms of the overall fit of the model. So I do want to mention too that as you're looking at those coefficients, just keep in mind that technically speaking, the value itself is reflecting the predicted change in logits per unit increase on the predictor variable. So you're not really modeling the relationship between the predictor variable and the predicted probabilities directly, but rather you're modeling them through logits. So logits are nothing more than a transformation of probabilities. And the reason why we're using logits instead of probabilities is that probabilities are bounded at 0 and 1. So the relationship between our predictors and probabilities cannot be linear because, you know, at some point if we were modeling as a linear function, the probabilities could actually exceed 1 or be less than 0. And that doesn't make a whole lot of sense. So what we're doing is we linearize the relationship between our predictors and the probabilities through logits, and so those values then are reflecting the predicted change in logits per unit increase on the predictor variable or the independent variable. But just keep in mind that the positive values and negative values still convey information about whether the predicted probabilities are increasing or decreasing with increases on the predictor variables. So now let's generate our odds ratios. So I'll go back to binary outcomes, logistic regression. We'll go into reporting and select report odds ratios. And so now you can see that we have our column of those values that are given right here. Just keep in mind that the z value and p values that are given right here, that's going to report on this, that's basically going to be the same as what we had above. So you're not going to need to report on significance tests for the unstandardized regression coefficients and odds ratios twice. You only need to report once. So at any rate, when we're looking at the odds ratios, basically they are related to the unstandardized regression coefficients through exponentiation. So if we exponentiate the coefficients that are given right here, that's what's going to give us the odds ratios here. And by the same token, if we take the natural log of the odds ratios, that returns us back to the unstandardized regression coefficients in this table. Now, I do think it's important to note that when we're talking about odds, what we're basically getting at is a ratio of probabilities. So a lot of times folks confuse odds and probabilities. They are related, but they don't actually mean the exact same thing. So when we're talking about odds in the context of our study right here, we're talking about the odds of a student passing, which where basically y is equal to 1. So the odds of a student passing is computed as a ratio of probabilities. So it's the probability of a student passing a test, so that's the probability that y is equal to 1, over the probability of not passing the test, which can be denoted as 1 minus the probability that y is equal to 1. So as you can see, when we talk about odds and probabilities, again, they are related to each other, but they're not, they don't actually mean the same thing, because odds are a ratio of the probabilities. So when we're looking at the odds ratio that's given right here, these are reflecting the predicted multiplicative change in odds per unit increase on the predictor variable. So for mastery goals, you can see that coefficient, the odds ratio is 1.1, which is indicating that for every 1 unit increase on mastery goals, the odds are predicted to change by a factor of 1.1. When we look at the odds ratio for anxiety, it's 0.922, so that would indicate that for every 1 unit increase on anxiety, the odds are predicted to change by a factor of 0.922. And that actually, because that value is less than 1, that would indicate decreasing odds, whereas the odds ratio right here, because that value is greater than 1 for mastery, that means that the odds are increasing with increases on mastery goals. Okay, so now let's look at some other ways of evaluating fit. So we'll go to statistics and scroll down and look at post estimation. We'll click on that option, and we're going to click on specification, diagnostic, and goodness of fit analysis, and I'm going to go to goodness of fit test, and I'm going to select where it says Pearson or Hosmer-Limashow goodness of fit test. I'm going to select Hosmer and Limashow right here and click on OK. So both of those are tests that can be used to evaluate the overall fit of the model. My preference is going to be the Hosmer and Limashow, but you could report on either or both of them. That would just provide some additional information on fit. And the Hosmer-Limashow test is basically using a chi-square test, and if this test result is non-significant, as it is right here, that's actually an indicator that our model is at least an acceptable fit to the data. So you can see right here that when we take that in conjunction with our chi-square test previous, or likelihood ratio chi-square test, both of those are indicating that we have at least, like I said, an acceptable fitting model. Although the pseudo R-square value is on the low side, so even though we have sort of an acceptable fit, we don't really have a strong fit of our model to the data. Now, another way that we can evaluate our model is to look at the classification accuracy for it. So I'll click on classification table with sensitivity specificity results right here, and we'll go ahead and select OK. And so now we get our classification results from our model. So basically what we're doing is we're generating predictions in terms of group membership, and then looking at the correspondence between predicted group membership and actual group membership in terms of our outcome. So as you're looking at this table, you'll see that up here it says true. So these are the outcomes that are observed. So the columns that are given are reflecting the outcomes that are observed. So the D column is reflecting the students who were observed to pass a test, and the not D that's given right here is reflecting the students who were observed to not pass a test. So you can see down here in the total, 245 students were observed to pass a test and 180 students were observed to not pass the test. Now over here where it says classified, we have a positive sign and a negative sign. So in the total column that's given over here, the first value for the first row is 307. That's the number of students that were predicted by the model to pass the test, and then we had 118 students were predicted by the model to not pass the test. So now when we look in terms of the correspondences, you can see right here that we had 198 students that were observed to pass a test that were correctly predicted to pass a test, when we had 71 students that were observed to not pass a test who were also predicted to not pass a test. So these values are reflecting accuracy and prediction, and on the off diagonal right here, the 47 and the 109 reflect the number of cases that were misclassified based on our model. So we had 47 students that were observed to pass a test that were predicted by the model to not pass a test, and we had 109 students that were observed to not pass a test that were predicted by the model to pass the test. Now, a couple of indices that are commonly reported in the context of this table right here is the sensitivity and specificity for the model. So that's what's given down here. So in terms of the sensitivity of the model, you can see right here it's 80.82%, and then we have the specificity is 39.44%. So the sensitivity is basically involves going to this column right here and taking the 198 cases that were observed to pass a test and that were predicted to pass a test, and basically divide that by the total number of observations that passed the test. So when we form that ratio and multiply it by 100%, you can see that 80.82% of the cases that were observed to pass the test, they were correctly predicted to pass the test. And then with respect to specificity, we would take the 71 right here, divide by 180, and then multiply that by 100%, and that gets us the specificity of 39.44%. So in other words, of the 180 individuals who were observed to not pass the test, 71 were correctly predicted by the model for an accuracy rate of 39.44%. Okay, one other thing that I wanted to show you before we proceed with example 2 is that we can generate predicted probabilities and predicted group memberships for the individual cases. So to generate the predicted probabilities for the cases, we can go to statistics, go back down to post estimation, and select predictions, and we'll go under this button right here for probabilities, influence statistics, residuals, etc. So it's actually under this that we could also generate various regression diagnostics for evaluating our model. But we're going to stick right now with just the predicted probabilities of a positive outcome. So that's the default that's given right here. And so what I want to do is I'm going to name a new variable for the data set. So I'm just going to name this P for probability. I could give whatever name I wanted to. But when I select OK, you'll notice that nothing really happens in the output, but when we scroll down in our variable list, now we have that variable that's reflecting the probability of passing our test. So from there, if we go into our data set, and we kind of scroll over, you can see that we now have a column of values reflecting the predicted probability of passing a test for each individual student. So that's based on their responses to the three independent variables in our model. And if we want to generate predicted group memberships, it's very easy to do then. We would use the command line, and what we'll start off with is just creating a new variable. We'll use the generate command, and then I'll give a variable name. I'll just call it PRGP for predicted group. I'll set that equal to, a dot, or basically a period. And when I hit OK, or enter, excuse me, then you'll see that it says generate PRGP, and it says 425 missing values generated. So a new variable has been created, but it contains nothing but missing values right there. But there's our variable in our variable list. So what we're going to do is replace those missing values with predicted group memberships. So to do that, we'll use the command line again and type in replace, and then we'll follow that with the name of our group variable, which is PRGP, and then we'll say equals 0 if p is less than 0.50. So in other words, we're instructing Stata to replace those missing values with a value of 0 if the predicted probability from that variable we just generated above is less than 0.50. So when I hit enter, you'll see that it says right here 118 real changes made. So now we'll do the same thing for group 1. So we'll type in replace PRGP equals 1 if p is greater than or equal to 0.50, and we'll hit enter, and so now those remaining changes have been made. So when I go back into my data set and take a look, you'll notice that now we have predicted group membership based on our model. So you can see that again, these are derived from the predicted probabilities that we generated in this column. So now let's go ahead and incorporate income level in our analysis. So this is example 2. So we're going to go to statistics, binary outcomes, logistic regression. I'll go ahead and go back under reporting. I'm going to stick with report estimated coefficients first. We'll go into model, and right here we can either use the drop down or type it in. I'll just go ahead and type it in. I'll type in income lev right there. Now at this point, the program's not going to recognize this variable as a factor variable. So what I'll need to do is to use the I dot prefix in front of it. And so by using that I dot prefix, it's going to instruct the program to perform that dummy coding that I was referring to earlier. So it's going to create 2 dummy variables that are reflecting group membership. So now when I press OK, you can see in our output that we have those dummy variables that are created. So there's the medium income and high income, and that's actually just reflecting the labeling in the data set. If you're going to go back into our data set right here, let me get rid of that, and we go to income level, you can see that the medium income had a code of 2, low income had a code of 1, and then high income, that was our value code, code of 3 right there. So that's reflecting the labeling associated with those value codes. And at any rate, let's go ahead and just kind of look at the overall fit of the model. You can see using the likelihood ratio chi-square test, we have statistical significance, which is indicating that our model represents a significant improvement in fit over the null model. The McFadden pseudo R-square value is 0.0806. It's not much greater than what we had before when we just had our 3 predictors in it. And then kind of looking at the individual predictors in our model, you can see that mastery goals was a positive and significant predictor of the probability of passing, whereas anxiety was a negative and significant predictor of the probability of passing the test. Interest, as before, was a non-significant predictor in the model. Now when we look at income level, you can see that both coefficients are positive, and as I had mentioned earlier, basically these are reflecting the difference in predicted logits between the 2 groups. So, but the positive value is indicating right here that students in the medium income category had a greater probability of passing the test than students in the low income category. And the same would be true for this case right here, where we have a high income variable. The slope is positive, and that would indicate that students in the high income category had a greater probability of passing the test than students in the lower income category. And both of those comparisons are statistically significant. So now let's just go ahead and generate our odds ratios. So I'll go back to binary outcomes, logistic regression again. And then reporting, we'll select report odds ratios. And so I've already kind of talked about interpretation of the odds ratios when we're dealing with continuous predictors. So we'll go ahead and just kind of move on and talk about the odds ratios briefly for these dummy variables. So the first odds ratio that's given right here is basically indicating that the odds of passing the test for students who are in the medium income category are 2.715 times greater than the odds for those students in the low income category. And then when we look at the odds ratio for the second predictor right here, the high income predictor variable, then that odds is indicating that students in the high income category were 3.6 times greater than the odds of passing for students in the low income category. Okay, so now let's go ahead and round out things with our Hosmer and Lemus-Show test and the classification results. So we'll go back to statistics, we'll go back down to post-estimation, and the specification, diagnostic, and goodness of fit analysis. We'll select goodness of fit test. We'll leave it set for Hosmer and Lemus-Show and click on OK right there. And as you can see right here, the test result is indicating non-significant. So that's again indicating that we have at least an acceptable fitting model to the data. Then when we look at the classification table that's given, or classification table option, we'll select report various summary stats and classification table and so forth. We'll click on OK. And so with this we get our sensitivity and specificity. Again, you can see that the sensitivity for the model is 83.67%, specificity is 40%. So you can see that the model is just generally doing a better job of predicting the probability of passing than predicting the probability of not passing a test. So it is demonstrating sort of differential performance in terms of prediction of outcomes. And then finally, when we look at the overall classification accuracy, it's 65.18%. So overall, we don't really have very good prediction, but as I noted just a second ago, we seem to be doing a better job of predicting the probability of passing a test than not passing a test. Okay, so that pretty well wraps up this presentation. As I noted before, be sure to download a copy of the PowerPoint that contains more information that you might find useful. I appreciate you watching, and you guys have a great day.